this 𝐸M seminar series, and I will be the host for today's talk. My name is Dibesh. I'm a researcher at 𝐸M, and let me allow me to introduce our speaker for today, Mr. 𝐸𝐿 𝐒𝐞𝐦𝐢. He is a doctoral candidate. He's a doctoral candidate in Indian Institute of Technology, Roorkee. And Ravi is a recipient of several prestigious scholarships and awards. And Ravi was here last week to attend this water security and climate change conference. And we took this opportunity to invite him in AIT, our campus, to learn about what his research is about, to discuss with him what we do here in 𝐸M, and also to see if there is any possibility of future research collaboration. Ravi's recent researches involve analysis of hydrometeorological characteristics from very interesting perspective of information theory, complex network, and other computing techniques. Like these are the very new topics for us, because we normally resort to the very traditional approach of analyzing hydrometeorological characteristics, right? So this is a new thing and very interesting thing to us that Ravi is going to present today. And from his doctoral dissertation, he has published several journal articles in reputed international journals. Now, for today's talk, Ravi will present one of his papers, which is on spatiotemporal variability of rainfall using an entropy approach. So without any further ado, I would like to invite Mr. Ravi at the front of this classroom to present us his talk. And Ravi will go through some of his slides, and he will take some questions from the audience after the presentation is complete. So if you have any questions regarding Ravi's presentation, please keep it towards the end of the talk. And for those of you who have joined this seminar online, you may type your questions in the chat box. So at the end, I will read those questions and present it to the Ravi. Now, Ravi, you have around 30-40 minutes to present, and the floor is yours.
Thank you, Dr. Dibesh. And I thank all who has joined this course in person and in online. So people in online, can you verify, do you able to hear me? Am I audible? Okay, thank you. So myself, I'm 𝐸𝐿 𝐒𝐞𝐦𝐢. I'm a Prime Minister's Research Fellow at the Indian Institute of Technology, Roorkee. So today I'll be speaking on understanding the variability of rainfall in space and in time using entropy. The aim of the talk is threefold, as I've mentioned. The first thing is to introduce the concept of entropy, and then using entropy, how we can analyze or investigate the variability of rainfall, and then to understand the climate change impact on rainfall.
Slowly it will give this kind of problem. Can you try that? It's working.
Okay. So climate variability versus climate change. So we often do confuse between the words climate change versus climate variability. So climate variability is a natural phenomenon, and it is a part of the climate cycle. Whereas climate change is induced by external factors, and the system cannot go back to its original position. Say, for example, if we cut a tree, or if we bend a rod by using external force, the rod cannot come to its original position. So in a similar way, we have hydrological components. If we induce more pressure on that particular system, it cannot come back to its original position. A good example from hydrology is groundwater extraction. If we extract more from a particular observation well, if we overexploit, then the recharge to that particular well is gone. Okay, so that we can term it as like a change, so which cannot go back to its original position. So climate variability, it's referred to a fluctuation or deviation from a normal climate. So for example, we have those variations can be caused due to the changes in the system, say for example, solar system, solar cycle, and it's a normal phenomenon. So consider this time series. So we have these observations. So even though there are ups and downs, I mean, either positive anomalies or negative anomalies, more or less the long-term mean remains stable. So this we can term it as climate variability. So climate change, as I mentioned, it's a permanent shift in space and time, and the values go outside the normal range of the natural climate variability. And the causes can be classified into two. One is natural, another one is anthropogenic. So this is in the era of Anthropocene, like mainly the land use change, the aerosol content and the CO2 is the primary cause for the permanent shift. So in which variables we can see this change? Mainly in precipitation, in sea surface temperature, and soil moisture. So we will be focusing mainly on the precipitation for this today's talk. Okay. So when we talk about precipitation, there are many characteristics that one should look into. One is total precipitation in a year, or what is the maximum precipitation or intensity. The most important thing that we are going to see in today's seminar is the spread of rainfall. How the spread of rainfall is changing in space and as well as in time, and what is the effect of climate change on the spread of rainfall. So to measure the spread of rainfall, what are the traditional measures we are having? So from the standard deviation, we can quantify the range. Say for example, the distribution of the data, but we cannot comment the spread of the rainfall. On the other side, range as well. Like from the range, say for example, if we consider this following numbers, the range is like maximum minus minimum value, which is 10. From this observation, we cannot really comment like in how many days the rainfall has happened. Similarly with the IQR range. So the scientists have come up with this concept of entropy to measure the statistics within the data. Say for example, when we consider two boxes, the first box is completely ordered. So it is said to be the box one is having less entropy. So entropy is a measure of disorderness. So in the box one, we can see the entire system is in complete order state. So there is less entropy in this system. On the other side, in this particular box two, it is complete chaos, right? So box two has more entropy. So we will consider an example and then we'll see how to interpret this entropy. Okay, so the definition goes in this way. Consider a discrete random variable x with values x1 to x2, so on up to x1 with respect to probabilities p1, p2, p, and so on. I'll come back to this formula, but the formula is probability of that particular event multiplied by uncertainty of that particular event. And then summation of first event to last event, okay, which represents the physical meaning is the average information content. I'll come back to this definition by considering an example. Okay, so let us consider a state capital X, which consists of events 20, 0, 0, and 0. Now we are deriving the probability for these events. So here the probability is defined as amount of precipitation of that particular event divided by total amount of precipitation. So 20 divided by total amount of precipitation is 20. So 20 by 20 is 1. And for the remaining events, it is 0. Now, if we are given with this system, how to calculate entropy? So the first step is to derive the entropy. So if I consider 4 events, P1 multiplied by log of P1. 1 multiplied by log 1 is 0. And rest among is 0, 0, and 0. Probability is 0. Now we need to consider the summation. The loop 1, 2, 3, 4. And then we estimate the total entropy. Okay, this is H1, H2, H3, H4. As I've mentioned, this particular log of Pi is the measure of uncertainty about the event happening with probability Pi. Okay. Upon summation, we'll get total entropy as 0, which says that minimum uncertainty about the occurrence of the event. So from the entropy value, we can say that there is no uncertainty in this particular system about the occurrence of the event. So the probability of a certain event is 1 and all other events is 0. So we have complete information about the occurrence of the event. Now, if we consider a different example, where in each, so now we have a system which is uniformly distributed. So calculate the probability for these events. So 5, total amount of precipitation of that particular event divided by total amount of precipitation. 5 by 20, which is 1 by 4. Okay. So 1 by 4, which is 0.25 multiplied by log of 1 by 4, which will give us a value 0.25. And then upon repeating the task from first event to last event, I is equal to 1 to n, we get h is equal to 2. So 0.25, 0.25, 0.25. And then the total entropy is 2 for this system. If h is equal to h max, so let me explain about h max. H max is the maximum entropy. Okay, the formula for maximum entropy is log n. Log n, where n stands for number of events. Here we have 4 events. So log 4 is 2. So when entropy becomes maximum entropy, then we say maximum uncertainty. That is, probability of all the events are equally likely. So we have no information about the occurrence of the event. For example, if I ask to a person with this distribution, can you say about the occurrence of the event? This is my distribution. Then the person calculates the entropy and he says that the entropy has become maximum. I mean, the entropy is equal to maximum entropy. So I don't have any information about the occurrence of the event. So to know about the information about the system state, there is no theory or there is no formula. And then the scientists came up with this formula of entropy, concept of entropy, to measure the amount of information about the given state. So to know the system state, if we apply entropy, then we can comment on the uncertainty, whether uncertainty of the occurrence of the event, from maximum uncertainty to minimum uncertainty, maximum entropy to minimum entropy. So viewed in this manner, for a fully deterministic random variable, this is the first case. We get absolute uncertainty, entropy is 0. On the other side, for the uniform distribution, where the occurrence of the event is likely, we have maximum uncertainty. So the range of entropy varies from 0 to log n. Now, say for example, if we have 365 days of rainfall, what is the maximum entropy from this formula? Say, okay, I have 365 events. The maximum entropy is log 365. If it is a leap year, log 366. If I want to compute entropy at monthly scale, I have 12 events. So the maximum entropy is log 12. If I want to compute entropy at seasonal time scale, 4 seasons. So log 4. So the maximum entropy, where it depends on the number of events. Okay. If it is monthly, 12, log 12. If it is seasonal, log 4. If it is daily, it depends on the other leap year or non-leap year. So from this, I see a limitation with this approach of entropy. Say, for example, if I want to compare the variability from daily scale to monthly scale, if I want to compare the entropies at daily scale to monthly scale, the maximum entropy at daily scale is log 365, maximum entropy. Whereas for monthly, it is log 12. So now can I compare? I cannot compare because the range of the entropy is varying with respect to number of events. So this is the limitation with this formula. So what I have proposed in my study is standardized variability index. Standardized variability index, which is defined as entropy, maximum entropy minus entropy obtained divided by maximum entropy. So I'll consider an example, simple example. Okay. So monthly time scale log 12, daily time scale log 365, seasonal time scale log 4. Now this is the maximum entropy, H max. Now I obtained entropy, say some x1, x2, x3. Now what I have did is I have normalized. So entropy, maximum entropy minus entropy, and so H max divided by H by H max. Upon doing this, the range of the value will now become 0 to 1. So now when I calculate entropy at monthly time scale using this formula, it lies in between 0 to 1. Similarly, for daily scale, it lies in between 0 to 1. And for seasonal time scale, it lies in between 0 to 1. Okay. So this is the first advantage of the measure. When we want to compare the variability across time scales, using simple entropy, it is not possible. We need to normalize that entropy for comparing the variability across time scales. Okay, this is the first advantage. Now I'll go to the second advantage. The second advantage is we have looked at the variability within a year. Okay. How about variability across the years? Okay, that we call it as inter-year variability. Within the year, it is intra-year variability. And across the years, it is inter-year variability. Okay, inter-year variability, say for example, I'm having a data with 100 years. With 100 years. But a client comes with 60 years of data. Okay, 60 years, I mean, a client comes with a case study where he has a river basin and he wants to study the inter-year variability for all the stations within that river basin. Okay, but the challenge is at every gauge station, the number of years vary from one station to another station. Say, for example, gauge station 1 has say 38 years of data. Gauge station 2 with 25 years. It's possible, right? When we talk about real-time scenario, it is possible. Right? In a given river basin, we don't have like equal amount of data for all the gauge stations. So for that scenario also, say for example, 38, 25, and 20. Now, if I want to compute the variability across the years for a June month, for example, for a June month. Now I have 38 events for this particular station 1. Then the maximum entropy is log 38. Now for the station 2, the maximum entropy becomes log 25. And then for the third station, the maximum entropy becomes log 20. Now again, here we see a challenge, how to compare the variability for these 3 stations. Because the maximum entropy is different. Okay. So here also, if we apply that concept, SVI, maximum entropy by log 38 minus entropy obtained by log 25 minus entropy by log 20. Then it becomes feasible to compare the inter-year variability. Okay, so this is the second advantage with this particular measure. Okay, so using this SVI, we can comment on how variability is varying across the time scales and how variability is happening in space. Okay, so in space and in time, using this SVI measure, we can really understand to how many, say, let us consider an example, one more example for a better understanding. So we have talked about the main aim of entropy is to look at the spread of the rainfall, in how many days the rainfall is happening, right? So if I go back to this previous example, so from this formula, from this answer, I would say that the rainfall is happening in all the days. The rainfall is happening in all the days. So the spread of the rainfall is 4. In the previous example, the rainfall is happening in only 1 day. So using this concept, we can comment on in how many days the rainfall is happening. So that is why we say here, viewed in this manner, Shannon entropy can be used for measuring variability. So variability in the sense, in how many days the rainfall is happening. Within 365 days. So apportionment entropy, which measures the distribution of rainfall within a given year. Okay. So we have 365 days, total amount of rainfall is capital P, and amount of rainfall within a given year is small pi. Okay. So the likelihood is amount of rainfall on the given day divided by total amount of precipitation. So I is equal to 1 to NC. NC stands for the number of days. If it is leap year, 366, non-leap year, 365. So, and then here I have mentioned, if I look at seasonal time scale, NC becomes 4. If I look at monthly time scale, NC is equal to 12. So entropy, apportionment entropy measures the intra-annual rainfall distribution. Intra-annual distribution. So we have looked at the advantage of this SVI, right? So the range becomes 0 to 1. 0 corresponds to no variability. Okay, so now this is very much important. This is very much important. Okay. So here in this case, on the left side, we got maximum entropy as 2, right? 2. 2 minus 2 by 2 is 0. So SVI value is 0 for the maximum uncertainty case. That is uniform distribution. Rainfall is happening throughout the year. On the other side, entropy is 0. So 2 minus 0 by 2, which is 1. That is 1 corresponds to maximum variability. Maximum means the entire rainfall is happening in only in 1 day. So this is the interpretation of SVI. If SVI is 0, It's a more or less a uniform distribution. If SVI is 1, there is high variability. Okay. So you can understand now from 0 to 1, if the value is around 0.5, we say that like out of 365 days, it's like the amount of rainfall is happening in approximately like half of the days. Okay. If it is near to 0, a hypothetical case where the rainfall is happening throughout the year. If it is 1 to only 1 day, out of 365 days, the entire rainfall is happening in only in 1 day. So is this clear, SVI? Now we proceed. So we have applied this concept of SVI to Indian rainfall system. So here I've considered 5 different examples, 5 different grid points to illustrate how it is varying with respect to seasonal timescales. Okay. So here we can see at the daily scale, more or less, the entropy lies in between 0.5, which says like out of 365 days, the rainfall is happening in 70 to 80 days. When we come to monthly time scale, there are certain years where only few months the rainfall is happening. Okay, and here when we look at the seasonal time scale for the third grid point, that too in which lies in the central India, almost then the SVI is 1. If SVI is 1, the amount of rainfall is happening in only in 1 season. It is true. In the central India, only in 1 season the rainfall happens, in the summer monsoon season. So this is the spatial distribution of SVI at 3 different time scales: daily, monthly, and seasonal. And the color bar shows the values in between 0 to 0.8. So during daily time scale, when we compare the variability in space, the northwestern India is having higher variability when compared to this eastern India and the Konkan coast, which says that the amount of rainfall is happening in very few days. The amount of rainfall is happening in very less days when compared to the other regions. When we compare the time scales from daily to seasonal, almost the color is red for the Konkan coast and the Gujarat region, the western parts of the country, which says that in the entire amount of rainfall is happening only in 1 season. Now, can we use this information to classify water resources? Say, for example, if we have good variability, say, for example, if the variability is very less, in most of the days, the rainfall is happening. And in addition, for those regions, if we have good amount of rainfall, then it is considered as a good class, class A. Class A says that there is a high amount of rainfall. In addition to that, the rainfall is happening in more than 50% of the days in a given year. On the other side, the regions with red color shows that the rainfall is very less, and also that amount of rainfall, that small amount of rainfall is happening in very few days. Say, consider the case of Thailand. Now, if we apply the concept of entropy and if we calculate the mean annual rainfall, we can also classify the water resources across Thailand. Okay. And not only that, if we consider global scale or the tropics or Bangladesh or Nepal, so upon applying this concept, it helps to classify the water resources based on the classification. Here, the dotted line is derived based on the 50th percentile. I mean, if we have calculated the mean of the mean annual rainfall to differentiate class A to class B. And here we have calculated the 0.5, the mean of the observed variations. So now for the case of, for the case of Thailand, for all the graded data, calculate the mean annual rainfall and then calculate the SVI, say consider a daily time scale, and then calculate the mean of total annual rainfall and then produce the dotted line. In the same way, in a similar way, calculate the mean of the SVI and then classify into 4 zones. Now, we can look now. The question is how the spread of rainfall is changing over a period of time. Is it stable or changing for a given? What's the effect of climate change on rainfall? So here we have considered a particular grid point to demonstrate the changes in rainfall days and then how the variability is happening. So when we look at that particular grid point, we have computed from 1901 to 2013, where the number of rainy days is very less when compared to the previous period. And the same information is getting captured in the variability. But now when we look at the total annual rainfall, there is no change, more or less there is no change in the total amount of rainfall. However, the number of days in which the rainfall is happening is getting reduced. So the spread of rainfall is getting reduced. It is getting narrowed down. So we are seeing like a very high spills in very less number of days. Further, this is an example. This is an example. The left panel shows the years before 1950, and the right panel shows the years after 1950. And then the amount of rainfall is more or less same for those particular years. However, in the recent years, we can see the amount of rainfall that is happening in this particular day. When see here the distribution of the rainfall, the same amount of rainfall is happening in like any number of days. However, now if we see into the recent years, a very high spell is happening. It's also the case with most of the grid points across India. So from this analysis, what I have studied is, what we have observed is, our null hypothesis is there is no change in the spread of rainfall. More than 30% of the land area has rejected that hypothesis, which says that the spread of rainfall is getting changed, it's getting decreased. And also we have looked at the condition with no change in total amount of rainfall. Here the case is there is no change in total amount of rainfall, but 30% of the land area is seeing a decrease in number of days. And in particular, most of the grid points are shown in the class A. Okay, earlier I've shown a picture with classifications, class A, class B, class C, class D. Now, most of the 30% of the land area is falling in class A, which is an alarming situation. Earlier, it is used to be a very good region. But these days, because of the climate change and anthropogenic behavior, the number of rainy days is getting reduced. So I have mentioned here, majority of the grid points falling under class A and class B are experiencing the reduction in number of rainy days, which implies that these regions will see high variability in the near future. So the analysis suggests that the class A and class B might move into class D and class C respectively, which is an alarming situation. So the overall takeaway from this talk is that how to employ entropy to calculate the variability at different time scales, daily, monthly, and seasonal, and then how it can be applied to classify water resources. And then upon doing basic trend analysis, we can get to know how the spread of rainfall is getting changed. And the concept is published in this paper, Journal of Hydrology. And we have also done a follow-up study with the same SVI, which is also published in Journal of Hydrology. And the origin of the concept has been established in 2001, which was continued by Mariuma in 2005, and then further in 2009. However, in these studies, they have worked with simple entropy. So when I was working with the concept of entropy, I have realized the limitations. We cannot compare across time scales and with different lengths of data. So there I have proposed this SVA and published in this particular journal. So more details and more better understanding is provided in this paper, and I would encourage you to read this paper. And yeah, I'm open to questions and for clarifications. Thank you.
Thank you, Ravi, for a very nice presentation and introducing this new concept of SVI for analyzing the spatiotemporal rainfall variability. I think this is very interesting, and this concept may be even more relevant in context of climate change, when the assumption of stationarity of the hydrometeorological parameters are no longer valid, and we can apply this approach and see like how the future variability in time and space will change under climate change scenarios. Thank you very much. Now we can take few questions from the audience. And I would also like to encourage the people who have joined online to please type any questions you have in the chat box. Anybody from the audience here? Yes. I think this is your opportunity to learn about the new approach. Like this is very new to us. Traditionally, like we resort to some statistical methods for doing this meteorological and hydrological analysis. Now here Ravi today has presented this new approach, which is very interesting. And for some of the students who will be doing their research in few months time, starting their research in few months time, this could be the area you may want to explore. Any questions?
Yes.
Thank you very much for your good presentation. I told you. My question is, have you checked with your approach in another country? Is it valid or not? If your research is in India, have you, like Bangladesh, have you compared with this, your formula? Is it valid or not?
I haven't compared across the countries. I did the studies only for the India. So that is what I'm proposing here. Apply this approach and then let me know how it is working for the other countries, say for Thailand, Bangladesh, Sri Lanka, Nepal.
Thank you very much.
I just have one short query. Probably you may have presented during your slideshow, but maybe I have missed it. Like you have chosen a threshold for the SVI and rainfall to have these 4 classes. So how those thresholds were selected?
So the thresholds are calculated by considering the mean. Say for example, if we have total annual rainfall for all the grid points. So we have looked at what's the mean total annual rainfall for a country. And then we have defined the threshold by considering the average condition by looking at the overall country perspective for the x-axis. And for the y-axis, it's the same. We have computed the variability for all the stations across the country. And we have looked at the average perspective. And then we have divided into like 4 zones. It's not the case because in one of the earlier study, they have defined 8 classes. So it's again a research question. So we have attempted here by considering the means from a country perspective.
I think it might be even interesting to look how those zones might change under climate change scenarios.
Yeah, that we have looked into it. So what we have observed is 30% of the land area, which was in class A, is facing a huge decline in the number of rainy days. But the amount of rainfall is more or less same. Maybe test this hypothesis in the entire tropics. Maybe if someone wants to take up this as a master thesis, I would encourage to look at the tropics and then apply the concept and then see how the total amount of rainfall is changing over a period of time. And then look at the total number of rainy days in which it is happening and then see how it is changing. Maybe define some 8 classes or 4 classes and then see what's the impact of climate change across tropics, subtropics.
Yeah. I think the research Ravi has done is the analysis of the past climate over the period of time. But we may extend this analysis for the near future. For example, if you want to look into 2020 to 2050 under different climate change scenarios, then we can replicate this study and see how those zones are changing. So we may find out that the region which was in zone A now change to, or in future might change to zone B or zone C. Or if you have higher number of classes, then that could be like one interesting research that these first year student might want to explore in their research thesis.
In addition to that, I would also suggest for a given country, maybe considering CMIP6 data, try to understand like how well the CMIP6 is able to replicate the spatiotemporal variability when looking at the past data. So from this perspective, we can really question, are CMIP6 is able to simulate very well in this particular region or not? That's also, and then if they are able to do so, do it for future, how they are going to change in the future.
Thank you very much, Ravi. I think that is interesting presentation. Yeah, I have some questions. Maybe in WEM, we used to ask the students to ask the questions first, and then faculties will go, right? So maybe before we take the questions from online students, maybe I will ask. I have to go. That's why. So can you go to this slide number 21? I just want to understand how this. So there are 4 classes you have classified, right? So this is based on the annual average rainfall in the x-axis, and y-axis it is the average of 0 to 1, or it is actual.
Not 0 to 1.
Yeah, because it is not 0.5, right?
It's not 0.5. It's not based on 0 to 1. It's based on the total amount of variability. I mean, at a country perspective, what is the average variability?
Yeah. Okay. So that means it is between 0.2 to 0.7. So you calculated the average SVIs across all the stations.
Across all the stations.
That's the mean, right?
That's the mean. Yeah.
So here there are 4 classes. So you, how do you relate this with water resources? Because this is rainfall, right? So my question is, there are 4 classes you want to classify based on how the rainfall is occurring, whether it is occurring uniformly or it is occurring within a short time, right?
Yes.
So based on that, you have classified.
Yes.
But how you are relating this, these zones are 4 classes with water resources? Water resources is something like water in the rivers, water in the lakes, something like that, right?
So you are exactly correct. So here the classification of water resources means from the precipitation perspective alone. From the precipitation perspective alone, say for example, class A denotes a very high amount of rainfall and also happening in a huge spread. So that is why we classed it as we defined it as class A. Class A means okay, in that particular zone, a good amount of rainfall is available, and also it is happening in many days. So it's like kind of good quality zone. On the other side, class C, the amount of rainfall is less than 1120 mm annually, but it is happening in very short number of days. So therefore, it is kind of not so good region.
Yeah, so then we can say it is like spatial variability of precipitation, right? How
spatial variability of precipitation.
How we classify based on how it is occurring based on this index. Okay, so my next question is like this entropy approach you have explained. How this is different from SPI approach? In SPI also, we kind of normalize, standardize this rainfalls from different spatial locations and also from different temporal scales to compare, right? To compare across different space and time. How that is different from this entropy approach?
SPA is defined as a standardized value. Say, for example, in that particular given region during that particular year, to how many standard deviations the value is given a precipitation or a temperature. And then how it is different from SVA is, SVA says the number of days in which that particular event is happening. So here we are looking at the distribution of the data, whereas the SPA says during that particular year or during that particular period, to how many standard deviations the value is. So that is completely different, and this is different.
Yeah, but in SPI also we use, we fit the rainfall with the Gumbel distribution or something, and then we normalize, right?
Normalize,
So
yeah,
We
true.
do all those things. Yeah, maybe this
But
is,
using SPA, we
Yeah.
cannot quantify the probability of the events in how many days it is happening.
oh, that we can do with this.
That we can
entropy.
do with this concept of entropy.
Yeah, in SPI only we can compare.
We
how
can
this
compare
variability. How it is varying from 0 to 1. So based
True.
on that.
True. So this
Okay.
is different. This here we are commenting on the distribution of the data within a
Yeah.
given year.
Yeah. Okay, so the climate change aspects we can apply for the same concept. You already did, right? You said some 30% of the
Yes,
land
we
is-
did. Yeah.
For which scenario? This one.
This is not for a scenario. So we just hypothesize that the change is happening. We made our hypothesis such a way that it is because of the change in climate. So, but we did not consider any projection here. Say, for example, different scenarios like SSP1 or S. So we looked at 113 years of data, and then we analyzed, is there any change in the pattern or not? If there is any change, we hypothesized that it is because of the climate change.
No, this the data comes from historical data, right?
Historical data, yeah.
Then how we call it as climate change?
I mean, when we have 113 years of data, when a change is happening, we can comment, right? I mean, to comment on climate change, we should have like past that at least one climate normal, that is 30 years. Since we are having 113 years of data, so we are doing this analysis.
So this 30% something you said, can you go to that conclusion? So that is from the historical data only.
That's from the historical data.
Climate,
not from the climate change
projections.
Not from the projections.
I think if I understand it correctly, we have 113 years of data, and Ravi has divided this into 3 periods.
Okay.
The analysis for each period and see the last period, how much changes has been
Yeah.
with respect to the first period. So
Okay.
30% changes was maybe in the last period was compared with the.
So this one is from recent past.
Recent 3 decades.
Changes from recent past.
Recent 3 decades.
Okay, yeah, thank you. Thank you.
Thank you so much, Dr. Mohana here. I mean, your presence is, I really appreciate. Thank you.
Any more questions? Yeah.
Hello, it's me Sagar Sai.
Hi,
I
nice to
just
see you.
want to know that can SBI me use in groundwater level indication or something or like that, or SBI is particularly for the rainfall only?
SBI is for the discrete random variables. Discrete, it's not for continuous random variables. Yeah.
Thank you.
Yeah, thank you for that question. So we cannot apply SBI for this temperature or because the probability of the event is happening every day. So
Any more questions?
Thank you, Ravi, for nice presentation. I have just one question. Maybe I don't know about the data, how you acquired it. In the case of data scarce region, there are lots of missing data. Now, how this entropy thing will treat with the data that we don't have in case of missing values or something? Do you have tested it or not?
So in my study, I've used IMD graded data. So in general, IMD graded data is available. There is no missing data in the graded data. But however, say for example, if this concept needs to be applied for the stations with missing data, consider the data without missing values, say for example, for the last 10 years or 20 years. And then still, if there are other stations with big number of data, like say 40 years or 60 years, still the comparison can be made. That is the advantage of SPA. No, I did not do the comparison at basin scale. Yeah, but there is a book. I have published a book chapter where I've exclusively studied for one river basin, Krishna River Basin in South Peninsular India. Yeah. So in this study, I have compared. I did the analysis at entire national scale. So I did not felt like okay.
Yeah, this is I think a grid-based analysis
Grid-based
covering
analysis.
the entire India.
But still, as you have suggested, maybe I would look into the sub-basin scale, because in space, there is a possibility that variability might change. So thank you for that suggestion. Yeah. This is at 0.25 by 0.25 degree. Another, yeah, not one time scale to another time scale. So here there is no baseline to compare. We are comparing across the time scales. Okay, how the variability is changing. Say, for example, for the water resources planning, if they look at monthly time scale, the monthly time scale map helps us, okay, how the spread of rainfall is happening across the country. If they look at the daily scale, if for the planning is for at the daily scale, then the daily scale map helps. If the planning is at seasonal same scale, so there is no baseline here to compare. See, here we are looking at how the variability is varying with respect to time scales from daily to monthly to seasonal.
Okay, any further questions? Any questions from the online participants? If not, then I would like to thank Mr. Ravi for accepting our invitation to be a guest speaker in this 𝐒𝐞𝐫 seminar series. I'm sure that today's talk has been very useful and very beneficial to the students and to all, even to me. It's very useful to know that there is a new technique we can apply for this hydrometeorological analysis. And thank you everyone, those who have joined us in person and also in online for attending this seminar. And to show our appreciation, I would like to present Ravi with a small token of souvenir to remember us by.
Thank you so much. Thank you. Thank you
Okay,
so much.
with this, I would like to conclude today's seminar. We can have one photo. Thank you.
Thank you so much. Thank you everyone who joined online. Thank you.